We have a concrete slab here, which is supported by a group of beams, like these ones, and these are carried by columns on which we would like to calculate the axial load. Of course, these will be spanning in one way, like that, so the load will be carried to these beams and then transferred to the columns. So the new thing here is the partition walls. We have this partition wall going parallel to the short direction, and we have this partition which is parallel to the long direction. So we start as usual. We start with taking a strip in the short direction of 1 foot width, and that will be this. So this is 1 foot wide strip. This is 1 foot. And of course the uniform load is 125 pound per square foot. So if we take a section here, it will be like that, and of course these will have reactions these are the reactions, but we need also to make sure that this strip represents both bays. If you look at this bay, you will see this is possible representation for this bay, except the area where the partition is, and the partition width is, this width is at best is about 4 inches, which is a quarter of a feet. So it is not, this is the only exception to the entire bay. So we can ignore this, and the rule is if you have the partition parallel to the short side, then what we do is we'll leave the calculation of this partition to the stage of beams. This is a rule, so if you want, you can write this down, that when partition is parallel to the short direction, it will be considered only at the beam level. So back to previous learning, we said this is 125 pound per square foot, so each foot is 125, so this means this is uniform load, which is 125 pound per foot length. This is 125 pound per foot length, and we said the partition will not be considered at this stage. Now, of course, this is not going to be representing this part of the bay, because this part of the bay has this partition wall, so that's why we need to take another red strip here. So we'll do another red strip here, and it will be like that. And if you look at this strip, this should represent this bay, and of course this strip would represent this bay. So you need to take 2 strips, and this will represent each and every movement here. So let's take a strip, so meaning that we'll need to take 2 strips at this case, one like that and the other like that, and then we have the reactions. This will be one reaction, and this is the other reaction, and this is the other one, this is the other one. And again, if you look at if we take a section like we did before, let's just make these reactions. If we take a section, of course this section was for this strip, and this section should be for this strip. So now what you see, of course, the uniform load is the same, the case as before. So this is the uniform load, and it's 125. But when we take a section at this point, you'll see this partition wall will show as a point load, like that, and the value of it is, say, 6.5 per foot length. So I can write this as 6.5 kips. And of course this is 125 pound per foot length. So this is the first stage that you have to make sure you get it right here. And of course we can, let's just update this with this will be RG1, this will be RD1, this will be RD2, and this will be RA1. And the same thing goes for these. This will be RI1, RF1, RF2, and this is RC1. So once we are done with this stage, and this will give us the values, this one will give us the values at this point, and when we add these two reactions we get the value at this point, and this reaction will give us the value at this point. And this side, this reaction will give us the value here, and these two will give us the value at here, and of course this will give us the value here. So we need to calculate these first, and then we move to each and every beam on the long direction. So let's do this first. So we'll start with the RG1 and RD1 and RD2. So let's do that on a separate. So RG1, RD1, RD2, and RI1. And the calculation here is straightforward. So it will be let's do this. So RG1 is equal to RD1 is equal to WL divided by 2. Of course this is W, and is equal to, so we have the uniform load is 125 pound per foot multiplied by 12 feet and divided by 2 is equal to 750 pounds. So this is the first reaction for this and for this. Now we'll do same thing to this side. So RD2 is equal to RA1 is equal to, again, omega divided by 2. Of course this is same, the omega. So W same, so it'll be 125 pound per foot multiplied by 15 feet and divide by 2 is equal to, so is equal to 937.5 pounds. This is the second value. As we have learned from previous example, the reaction at D will be the combination of both RD1 and RD2. So RD is equal to RD1 plus RD2, which is 750 pounds plus 97.5 pounds, and the answer is, I will ignore the decimal, 1687 pounds. So that is the value. So that's the first strip that we calculated. So we'll move to the second part. The second part will be the other side, which is same. So I'll have same goes RI1 is equal to RF1 is equal to omega L divided by 2, which is, this is the omega or W, and same thing goes for this one. So is equal to 125 pound per foot multiplied by 12 feet divided by 2 is equal to is equal to 750 pounds. Now for this side, it is a combined case of two loads. So this is equal to two beams. So one beam is uniform load only, with uniform load only, and the other will be, so we'll do this, which is equal to, now we'll call this, we'll name this RF21, and we'll name this RC11, and this is equal to RC11 is equal to WL divided by 2 is equal to 125 pound per foot multiplied by 15 feet 15 feet divided by 2 is equal to, so for this part is equal to 937 pounds, plus the other beam is a 1 new point load. So we have this, and the point load is at this here, which is 6.5 kips. And of course this distance is 5 feet. Now this reaction is RF22 and this is RC12. Now the RF22 and RFC12 are not equal, so this will be equal to, I need to go back to the charts, will be equal to 6.5 kips multiplied by the opposite distance, which is this one, 5 feet, divided by the entire distance, which is 15 feet, and this is equal to 2.166 kips. And for this one, RC12 is equal to 6.5 kips multiplied by 10 feet divided by 15 feet, and this is equal to 4.334 kips. Let's just highlight the values we got here. So of course we need first of all to add up these values here. The RF2 is equal to RF21 plus RF22 is equal to, this is equal to 937 pounds plus 2.166 kips. So we be careful. Okay, these are two different units, so we need to convert the pound to kips by dividing this by 1000, or the other way around. You can multiply the 2.166 by 1000, comes 2166. So with that one, I will write this is equal to F2 is equal to 5,000, I'll say, is equal, 3,103 pounds. Because I need to convert, this will be converted into, I'll say this will multiply by 1000, makes this pounds. and this needs to be converted into pounds. For this part, same goes here. So the RC1 is equal to RC11 plus RC12. So if you add up numbers, now again you have 937 plus 4,334 pounds. Again, I converted this into pounds by multiplying it by 1,000. So the answer for this part is equal to 5,271 pounds. So these are the new values I have. Now this is equal to this plus this, but the value at F is the combination of these two. So we'll do that here. So you see RF is equal to RF1 plus RF2 and is equal to 750 pounds plus 3,103 pounds, and we get this equal to 3,853 pounds. These are the new values. So I got all the values on the beam. So on beam IF it is equal to 750, and on beam and on the interior beam, which is the F, is equal. So let's go back to the sketch. Let's close these ones and get to the main and the results. So now we get values here. So these will be 750, so we can update these values as we go. So if you go to calculation 1, we have now we'll update the results on these beams. So this will be, we have this 750 pounds, and the intermediate, this will be 1687 pounds, and this is 937 pounds. This will be same as the previous one, which is 750 pounds. This is 3853 pounds, and this is 5271 pounds. So now we are ready to do the beams, because we found the values on the beams. So we can start with the, I'll do only 2 beams here, and the rest will be, so if I, same thing, I would do this beam, which will have this reaction, this reaction, this reaction, this reaction. So this will be like that. With the same concept, the uniform load will be, so you see when you project this value on this beam, so only on a width of only 1 foot, this is equal to 937 pounds. But you see this repeats all over the beam here. So this becomes 937 pound per foot uniform load. Of course, this is different because we have 2 strips, so just be careful. These are 2 different. So for this one, this is the value that will be projected here. If you project this, So you see for each foot the value is equal to 5271. So meaning that this will repeat like that. So this will be 5,000 pound per foot. Now just another reminder, see this partition was not taken care of at the level of short direction. So it means it will be taken care of at the level of beam. But this partition was taken care of at the short direction calculation, so this will not be considered in the beam calculation. Now how do we deal with the one that was not considered in the short direction? Is this partition, so half of this partition will go to this beam and the other half will go to this, and same thing goes here. The half will come to this and the other half come to this, and keep in mind this is 3.5 kip per foot. So based on that, this beam, which is, let's just write down, this is RA3 and this is RB3, this is RB4 and this is RC3. So this point load here is equal to whatever the value here is, which is 3.5 kip per foot. So this is 3 kip per foot multiplied by the half of the distance, which in this case 15 divided by 2, multiplied by 15 feet divided by 2. That will be the point load sitting on this beam. So I just need to make sure that we do these numbers when we do the calculation for the beam AB, because if we don't do that, then that is wrong. So just make sure that we understand this part clearly. Okay, and for this part there is not much of a problem. This is typical to what we did before. This calculation mean for the beam calculation will be straightforward because we already considered the partition and the structure. So I'll move to do the calculation for beam AB and B3. So I'll hide the sketch and start to do this. So just to confirm, this is equal to 3.5 kip per foot multiplied by 15 feet divided by 2, and the value of which is equal to 26.25 kips, because you see there's cancellation here. This foot and this foot will be cancelled, so I'll be left with kips. So now we have a straightforward case of two loads, uniform load plus point load. So we'll do that. So this is equal to the uniform load here. Well, there's so this reaction, we have this reaction, and we have the uniform load, which is, if you go back to the sketches, you see it is equal to 937. So the uniform load here is equal to 937 pound per foot for both of these, and of course this is W. So on that, so of course this is RA31 and this is RB B31. The calculation for straightforward is equal to RB31 is equal to WL divided by 2 is equal to 937 pound per foot multiplied by 22. This is 22 feet and divided by 2. So this will be equal to, Yeah, this is 26, sorry. This is 26. 26 will be equal to 12,181 pounds. That is the value for this part. Now we continue plus the point load. And we have the point load here, which is 26.25. And we'll do our calculation again here. Let me just make sure that we have. So this is RA32 and this is RB32, and the calculation will be a bit different. These are not equal to each other, so this is equal to 26.25 kip. The opposite distance is equal to 18 feet. By the entire distance, 26 feet is equal to 18.173, that is kips. Or if you will, it will be equal to 18,173 pounds. For this part, it is equal to, again, the load is 26.25 kip. The opposite distance is 8 feet. The entire distance is equal to 26 feet, and it is equal to 8.076 kips, equal to 8,076 pounds. That is for these calculations. Now we need to add these up, because as you know, this is equal to this plus this. So RA3 is equal to RA31 plus RA32, and is equal to 3 each to R is equal to 12,181 pounds plus 18,173 pounds, and is equal to, so RA31 is equal to RA3 is equal to 30,354 pounds. That is the load on column A. Now let's see how much is the value here. The RB3 is equal to RB31 plus RB32 is equal to. So we have again 12,181 pounds plus 8,076 pounds, and is equal to 20,257 pounds. That is RB3. Now back to this part. This part is straightforward. So RB4 is equal to RC3 is equal to WL divided by 2 is equal to. Of course, I think I made a mistake here. This W is not same as this one, because each beam is different. So this W, if you look at the sketch back, you will see this is equal to 5,271 pounds per foot length. So the omega is equal to 5,271 pound per foot multiplied by 22 feet and divide by 2 is equal to. So RB4 is equal to RC3 is equal to 57,981 pounds. So that is the axial load on column C. Now the column B will have the combination of these two, so we need to do that. So RB is equal to RB3 plus RB4 is equal to, so RB3 is equal to 20,257 pounds, and RB4 is equal to 57,981 pounds. So RB is equal to 78,238 pounds, and that is the axial load on column B. So we can say this is column B, this is column C, and this one is column A. You can continue with the same way of calculation for the rest of the beams, the interior beam and the other beams. So if again, if you got the results, so we did the calculation for this column, and for this column, and for this column. You can continue to do for these columns by doing the beams DEEF and GHHI.